Okay, again, my name is Jeff Behringer, my partner Max Haddon, and our project, I'd like to thank you all for coming today. Our project this semester was a SCADA design for a natural gas transmission regulator station for the Vectren company. Sorry, I'm wrong. I'd first like to note that due to the inclusion of some proprietary and security restricted material, some specific information has been intentionally censored from this presentation. Our project objective was to automate and monitor the regulation of gas pressure within a system of transmission pipelines through the design and installation of a new SCADA system for Vectren's gas control department. Vectren is currently serving approximately 1.1 million gas customers throughout northern and southern Indiana and central Ohio, as seen here. Our specific project directly impacted the Buxton area and operates between a purchase point in the north and a storage field down in the southern region, and it's located in Martinsville, Indiana. Okay, to give you a better perspective on the location, we're starting here at USI, and we're just going to go over to downtown Evansville to the Vectren corporate offices and Vectren engineering and gas control department. And then we'll pan out and go zoom in on the Martinsville Town Border Station where this project is located. Safety of the natural gas transmission industry is regulated by the United States Department of Transportation, Pipeline and Hazardous Materials Safety Administration, and has directly controlled the direction of the design of this project. Specific code defines pipeline design pressures at specified minimum yield strength, or SMICE, which is similar to a typical hoop stress calculation. It then evaluates the transmission pipeline as operating near pressures of 20% SMICE and defines potential impact radius around the system in the event of a leak or explosion of the system. It further defines high consequence areas within that radius where an accident would have a large impact on human population. Sorry. And seen here is the site location and its proximity to a known HCA. The gas pressure at this site is controlled by a regulator operating between pipelines of high and low pressure. On top of the regulator is what is a device known as a pilot, and that is, for the sake of this project, is being replaced by an automated pressure transmitter and actuator. The Martinsville Town Border Station has been tested up to 1,080 psi-G, has a maximum allowable operating pressure of 600 psi, and is operating at the low end around 160 and the high end around 350 psi. Seen here in blue are the design components, major design components of our program. We had a major focus on the remote terminal unit programming. Its retrieval of pressure data from the pressure transmitter, control of the actuator, and its communication to the SCADA network. Our project began with the component specifications and installation. We moved on to programming the remote terminal unit, and then operational program testing, and further testing within the SCADA network. The remote terminal unit was specified by Vectren and operates at about 1.5 watts. It was selected due to its modular design if the site was to ever be expanded. Our major project focus, again, was to assign the use of communication ports through the collection to collect pressure data, control the actuator, and communicate with gas control. The pressure transmitter and sensors have an operational range, temperature range, of -60 to 60 degrees Celsius. They have very low power consumption, and again operate between 160 and 350 psi with a maximum working pressure of 2,000 psi This unit then has a marginal safety of 4.7 based off the higher operating pressure range. The regulator position actuator was selected due to redundant position confirmation. It has a built-in 1 kilo ohm potentiometer and a 420 milliamp transmitter for remote communication. The data quality of the position is then further confirmed through the RTU programming. It was also selected due to as it has a continuous duty motor. It has a built-in reduction gear and it provides up to 100 inch-pounds of torque for positioning the regulator. The network communication system operates over a wide area network using the Bristol Babcock Network 3000 family of products. And it operates over a T1 carrier system at bandwidths of 128 kilobits per second. The total power requirements for all of these components comes in at just over 50 watts. And with these components selected, we then prepared the site with the installation of an oversized RTU housing to allow for further expansion of the RTU, installation of power and communication lines, and for a total footprint, not including the underground wiring, of about 10 square feet at the site. I'll now hand it over to Max to discuss the software side of our design project.
Okay, so one of the first steps in a project like this is sort of outlining the different aspects of the project that we're going to be doing in terms of how we need to use the RTU, what ports we have to use, what the functionality is going to be, and this will lead to our actual design later. But with this outline, we knew we wanted to measure the upstream and downstream pressures at the regulator station. We needed the valve state, which in this case the valve is the regulator. And we need to make sure that we can operate it either like fully open, fully closed, or somewhere in between to regulate the pressure, however we need to. We need a way to check data quality from the sensors themselves. So if we have a bad sensor or the readings aren't coming in how they should, then we need a way to flag that so that the operators know that something is wrong with the sensor. So any errors that arise aren't directly attributed to some sort of malfunction with the system itself. We also need a way to know its power status. So normally this will be powered from AC power. It has battery backup or a UPS system, just in case the power goes out. But we need a way to track whether it's on AC power, whether it's on its backup battery, or whether the backup battery has been fully depleted. We also need a way to have the operators override it if they're on site. So normally everything should just be automatic, but if operations has to go on site and fix something or adjust a valve or a sensor or anything like that, then they can flip an override switch will prevent any sort of high or low values from triggering alarms automatically as it would. So that just reduces the noise that gas control deals with so that they don't think that some part of the regulator station is failing. And the last part would be the user interface, and we'll actually have two user interfaces. One will be gas controls, and one will be the on-site. It's a two-line display that I'll get into next. And that's so that operations on-site can view the current real-time stats of the regulator station. So the next step in sort of this preliminary outline process is developing pseudocode. So that's a code-like text format where it's not actual code. In this case, we did write it in a textual format, but for visibility, we broke it into a flow chart. This sort of outlines the continuous loop that will be occurring within this regulator station, where first it determines whether gas control, the actual main SCADA system, is requesting its data. If so, Then it checks to see if the operator override has been activated. If it has not, then it checks to make sure that the sensor data is valid. And if it is valid, then we go through this sequence where we pull the upstream pressure, downstream pressure, valve position, the maximum pressure that the system can handle, and if there's a set point change. If there isn't, then it'll just exit the loop. If there is a change, whether it's an increase in pressure or a decrease in pressure, then there's an algorithm to increase it by whatever percentage it needs to be increased in order to reach the set point. And this is a continuous loop, so the main trigger is gas control SCADA system polling, trying to retrieve data, and that trigger is what causes this cascade to occur. So the IEC 61131, it's a standard for all PLCs, all SCADA systems, and there are various aspects of it. One in particular is the 5 programming languages. We ended up using just structured text and a function block diagram. You have all 5 of these options, and really they all work. You can use multiple types in the same program. You can use just one if you like. It really depends on what the project is and how best the coding format works to achieve what you want to achieve in the project. So we, again, used structured text and function block diagram, which I will go over a little bit. Because it's structured text in this slide, we didn't want to put too much on it so that you wouldn't be able to read it. So in this case, this is just a simple example of a percent error calculation. So you could get 2 input values and determine the percent error based on those 2 input values. And then in this case, for this example, we say if the percent error is greater than 10%, then we will set a data quality alarm to true. So potentially this could be used to sort of indicate that we have a data quality issue. Expanding on this example and going into a function block diagram, what you can do is actually use the structured text as the heart of the function block diagram, and then just define input variables and output variables. So in this case, we're expanding on the last percent error example. So there are 2 input variables and there are 2 output variables. The output is the actual percent error value, and then the flag indicating whether there's bad data. So as far as the user is concerned, whenever they are using this function block, they don't have to know anything about the code inside. They don't have to know how it works or why it works. They just have to know that there are 2 input variables and 2 output variables, so that they can potentially chain multiple blocks to make a full functional program without having to deal with the details inside. So with the software interface, this would be an example of the on-site interface. It's a simple 2-line display, and it just allows anyone who's on-site in the field to be able to page through the different values of the reg station. So it's just 2 lines, and because of that, there's more than 2 lines of data. So there's select buttons to allow them to scroll up or down, and then an override switch, which would be to prevent errors or alarms going off in gas control because they're doing routine work on site. And the gas control human machine interface, which is HMI, is actually a Prophecy iFix program. It's made by GE now, and it provides the link between the RTU and the HMI, and we actually had to define those links. This is an example, of course, parts of it are blurred, but you can actually see whether the values are functional. This was actually part of a testing sequence that we were running. So right now the sensors weren't hooked up, so we have some negative pressure values. But this was just to establish communication for us. And in reality, gas control customizes the user interface for however they would like to best see the data. So then we moved on to a communication and testing phase where we had to try to assemble the program. And this is the Emerson Control Wave IDE, which we use to make the program. The first step is sort of starting with different code blocks, debugging them, we have to make sure that each block functions before we integrate it into the full program. And some different errors that we have to watch out for are syntax errors, compiler errors, and communication errors that would occur as we're building the program itself. So ideally, once you compile the full program, you want to see 0 errors and 0 warnings. And this was the point where we were able to download the program into the RTU itself. And the next step would be the network function, in which we have to make sure that we can communicate with the RTU, because gas control here in Evansville is directly connected through that T1 line to the Martinsville regulator station. And in order to ensure that all of the values for our different sensors are being communicated back, we have to make sure that the network is up and we have everything linked properly. So here are some of our expenses. We have the RTU itself. We needed a router, the pressure transmitter, the RTU housing, and the actuator. And for programming, we have the design software and training, which is substantial, and then our time that we put into the project. And so this is the total, including everything. So it was just under $14,000 for this project. And we'd like to thank everyone at Vectren that helped us with this project. We want to thank everyone at USI who enabled this, and of course our own family for putting up with us. And so we'd like to open it up to any questions that anyone has.
All right, questions? Thanks. Max, you talked about data quality at one point, and you even showed a piece of sample code with a kind of the idea behind a possible data quality calculation. Can you talk more specifically about how you coded for data quality for your various sensors, how much work it took, what you ended up doing to evaluate data quality?
So that was actually one of the more complicated aspects of programming. It was a more recent addition to the different RTUs that are around the network. The idea behind it was to have an algorithm that would check the span and the deadband for each sensor, and then if the value that it was returning or if the value that it was reading was over 10% of the max span or below 10% of the minimum span, then it would be assumed that the data quality would be poor because these readings shouldn't occur in reality. And it could be further customized to sort of have an additional algorithm. We weren't advanced enough at that point to be able to do that. But this simple check is what the program uses to basically determine whether values are valid or not, and whether to even send them back to gas control or not.
Can you provide any insight as to why a router, which, you know, you can get at Walmart for $50, is over $1,300 for this project?
In reality, we're not really sure. I know that this is a legacy system. We are upgrading the network from this sort of asynchronous system to a more synchronous modern one. And this is the standard hardware that Vectren uses, so we're not really sure why, or if it's just because it's legacy hardware. But we did think that it was kind of unusual how expensive the T1 router is.
Has any part of this been installed?
Yes. Actually, everything has been installed. The last time we were testing, the only thing that hadn't been completed was the sensor communication lines from the pipeline itself to the RTU housing. So whenever we were testing, on that one slide, you could see that some of the values were negative, which didn't make sense. But that's really the last step, because you would of course test once the lines are connected to make sure that the values are valid. But other than that, the program is complete and all the hardware is on site.
All right, any other questions? No, let's give them a hand.